In this lecture, we'll discuss reflection and refraction at interfaces between dissimilar materials and the analysis of optical systems that may contain multiple interfaces. So apart from an isolated interface, we may be interested in something like this, an optical multilayer that may serve, for example, as a coating system for a lens to minimize reflections. This problem has a lot in common with the quantum mechanical problem about a particle moving in a stepwise constant potential, where we have to match the wave function and its derivative across the interfaces where there's a jump in the potential. Here, in the case of the optical system, instead of matching the wave function and its derivative, we will need to match the tangential components of the electric and magnetic fields. The methods that can be used to solve these two kinds of problems are essentially identical. We will use Maxwell's equations with no free charges. This is a very natural choice for dielectric materials, where all the charge and current densities are naturally included in the polarization and magnetization of the system. But in fact, this does not restrict the generality of our approach in any way, because conduction currents can also be formally represented as polarization currents and included in the definitions of the dielectric permittivity. We will deal with monochromatic waves so that the connection between E and D can be found using the frequency-dependent dielectric permittivity for the given frequency corresponding to the monochromatic wave, which can be complex. So there is no restriction here that epsilon has to be real. Same thing for B and H. And the values of epsilon and mu can, of course, be different in the different layers in the optical multilayer. As usual, we write the monochromatic fields in terms of their complex amplitudes. So then time derivatives are easily taken in the Maxwell's equations. They just give factors of minus I omega. Now we can write the two curl equations like this. And now, using the fact that d of r is epsilon times E of r, and b of r is mu times h of r, epsilon and mu are, of course, taken at the given frequency, then we can take a curl of, let's say, the first of the curl equations. So we'll have curl of E on the left. So using the usual rule, that will give us del of del E minus the Laplacian of E. But del E is 0 because of the other Maxwell equation. Del D is 0, gives us del E is 0. And then the right-hand side is I omega curl of B, which in turn is I omega mu times curl of H, which is minus I omega d of r, and that's epsilon E of r. So overall, this gives us the wave equation. The equation del squared plus epsilon mu omega squared E is equal to 0. And exactly the same expression will be found for B if we start with the curl of the other equation. The solutions that we'll need are plane waves. So we can write them as E of r equals the amplitude E naught and the harmonic exponent e to the ikr. If we substitute this in the equation, we'll find k squared equals epsilon mu omega squared. Now, from the curl equation for E, we can write that curl of E equals negative b dot, which is the same thing as I omega B, and then writing E and B both in this form with e to the ikr, we will find that k cross E naught should be equal to omega B naught. So this gives us the connection between the amplitudes of the E and B fields for the plane wave. Now let's introduce the wave number k, defined as k squared equal epsilon mu omega squared. Now, in terms of this wave number, we have k vector equal k times a vector n, and this vector has to have a property that n dot n equal 1. So if the vector k has all real components, then n is just a unit vector giving us the direction of propagation for the plane wave. But we'll allow a possibility that the wave vector k has an imaginary part. This will correspond to a wave that is evanescent. This will be the case where a beam of light is incident onto an interface under the conditions of total internal reflection, where all the energy is supposed to bounce back from the interface, but there will be an exponentially decaying wave on the other side of the interface. We'll see later how it comes about, but for now, let's anticipate that this will correspond to the wave vector n having an imaginary part, and we can introduce the real and imaginary parts by writing n prime plus I n double prime. And then because n dot n equal 1, we have two conditions. So if we write n squared, both real and imaginary parts should be consistent with the right-hand side. So we'll have n prime squared minus n double prime squared equal 1, and the product of n prime and n double prime is equal to 0. An imaginary part of the wave vector corresponds to our electric and magnetic fields blowing up exponentially in a given direction in space, which is certainly not allowed if the wave fills the entire three-dimensional space. However, if we have an optical system, the electric field can have pieces that depend exponentially on the coordinate perpendicular to the interfaces. The situation is entirely analogous to the quantum mechanical system where the particle tunnels through some of the regions. In that case, you have a superposition of two waves, one exponentially increasing and one exponentially decaying, but because this region is bounded, nothing is diverging anywhere. The boundary conditions at an interface can be found from Maxwell's equations. So if this is an interface, we can do two things. So to establish the boundary condition for the normal components, we take a pillbox straddling the surface. So if we look from the side, that's just a small area with two surfaces on either side of the interface. And then from the equations for the divergence, we'll find that the normal components of D and normal components of B on the two sides of the interface must be continuous. Here, L and R means the left and right sides of the interface. Now, for the tangential components, we have to consider a loop like this and apply the Stokes theorem using the curl equations. So this will give us that the tangential components of E and H must be continuous. So E parallel left must be equal to E parallel right, and same thing for the H field. Using the Stokesian loops in two orthogonal orientations will show that both parallel components of E and H have to be continuous. We will make explicit use of the tangential components, and the normal components will in fact be continuous automatically. Let's examine one interface in a system and consider the matching of the fields on the two sides of it. First of all, we notice that the matching of the plane waves on the two sides should involve only waves with the same projection of the wave vector onto the interface. So we have waves that look like E naught e to the I k r. Now, for the matching to be at all possible, the projection of k onto the plane of the interface have to be the same for all waves that are being matched. You can't make two sine waves with different periods equal to each other. So then, in our set of waves that are being matched, the k parallel, the projection of the wave vector onto the plane of the interface, has to be the same for all waves in question. In addition, this k parallel must also be real. It must be real because otherwise the waves would blow up in one of the tangential directions, and there's no boundary in that direction. Because there's no boundary, it would diverge. So this would be unphysical. So all waves have to be characterized by the same value of k parallel, which is real. Now the value is given by the wave vector of the beam that is incident onto the whole optical system externally. In a given region, on the left or on the right of the given interfaces, there may be two solutions of the wave equation with the same value of k parallel. They will differ in the signs of the normal component of the wave vector, which we call the z component. So in each region, we'll have two waves with k parallel plus kz and same k parallel minus kz, generally speaking. Here, k parallel must be real, but kz could be real or imaginary. In addition, we know that k parallel squared plus kz squared must be equal to the square of the wave number. Now, to remind, the wave number is related to the frequency as square root of epsilon mu omega. In vacuum, epsilon and mu would be replaced by epsilon naught mu naught. So we have k divided by k vacuum for the same frequency given by square root of epsilon mu divided by epsilon naught mu naught. Because the speed of light in a medium is given by the ratio of the frequency to the wave number, the ratio of k to k in vacuum for the given frequency gives us the ratio of the speed of light in vacuum and the speed of light in the material. This is defined as the index of refraction, and it gives us the relation between this index and the dielectric and magnetic permittivity and permeability of the medium. We can also write this relation as k, the wave number, equals n omega over c. Because k parallel is the same in all the regions in the optical system, we can align it with the x-axis, or rather pick the x-axis in the direction of k parallel, so that k parallel is then simply kx times x. Now we have seen before that if we write the total k as wave number k times vector n, so that n dot n equal 1, it follows that the real part and imaginary parts of n are orthogonal. This leaves us with two possibilities. The first possibility is that kz is real. In this case, we have a real beam, so we can introduce the sines and cosines showing the direction of that beam. The second option is that kz is purely imaginary. So if kz has an imaginary part, it follows from this dot product that the real part of kz must be 0. It can also be seen from this expression here. If k squared is real, which we assume in this discussion, then because k parallel is real, then kz squared is either positive or negative. So the square root is correspondingly either real or imaginary. If the medium is not transparent, that is, if epsilon and or mu have an imaginary part, then the wave number is itself complex, and then the distinction between these two cases is not really there. Then the kz is always a complex number, and then it makes no sense to make a distinction between the normal refraction and total internal reflection. That is only meaningful if the material is transparent. In the following, we will not assume anything specific about kz, whether it's real or imaginary or more generally complex. Whatever comes from this equation is what will appear in the following expressions, and this equation can be used to determine whether the given region has propagating waves or evanescent waves. Let me re-emphasize that while kz is different in different layers of the optical system, k parallel is the same for all of them. Let's now consider the simplest case of reflection and refraction that involves only one interface between two semi-infinite homogeneous regions. So there's a flat boundary, pick the z direction like this, and then we have an incident beam from the left, there's a reflected beam, and a refracted beam. We need to write the expressions for the electric and magnetic fields and match them at the interface, so we have the solution of Maxwell's equations that's valid everywhere. We introduce indices of refraction on the two sides of the interface, which will denote n and n prime in this case. And then recall that the boundary conditions are E parallel on the left, so we can call it 0 minus equals E parallel 0 plus, so immediately to the left and to the right of the interface, and same for the magnetic field. Now we notice that we can separately consider two different polarizations of the incident beam because of this boundary condition. One polarization is the one for which the electric field is aligned with the y-axis. So as a reminder, we picked the axis x to be parallel to k parallel. So k parallel is kxx. So there is no component of k parallel in the y direction. So one of the possible polarizations that we'll call perpendicular, with the electric field perpendicular to the plane of incidence, will have the electric field aligned strictly with the y direction. Now the magnetic field will then be parallel to the plane of incidence, and this orientation will be preserved in all the layers because of the boundary conditions. If the electric field has only y component in one layer, it has to have only y direction and the adjacent layers. The other possibility is electric field parallel to the plane of incidence. So then the electric field will have x and z components, but the B field will then be strictly in the y direction. So let's pick one. Let's pick the perpendicular polarization and work out the matching of the fields on the two sides of the interface for this specific case. So the x-axis goes like this, and then the fields are defined in this way. So there's a electric field perpendicular to the plane of incidence for every beam. We'll use this notation where the incident plane wave has the amplitude E, the reflected beam E double prime, and the transmitted one E prime. So then, generally speaking, all of these plane waves have the exponential k-dependent factor in them. So the incident wave, for example, looks like E y e to the I k r. Now, this factor contains the factor e to the I k r with k parallel and e to the I k z z. Now, the factor with k parallel is the same for all waves. We have established this before. Because they have to match everywhere, this factor is the same everywhere. So in the matching condition, we just drop it. It appears in every term. Now, this term, e to the I k z times z, will be set to 1 because we pick the 0 on the z-axis to lie exactly at the interface. So the matching is done at the interface, and at the interface, this exponent is equal to 1. So the matching for the electric fields looks explicitly as E plus E double prime equals E prime. This is the only tangential component for the electric field. Now, what about the magnetic field? Well, here we recall that the magnetic field, so B, in the same wave, is related to E through the curl equation, which tells us that B is equal to 1 over omega k cross E, where E is this amplitude here, E times y. Now, we can work this out and insert the components of k that are non-zero. So this is kx and kz. There's no ky, thanks to our choice of the reference frame. The electric field is E times y. So taking the cross products, so here I have E over omega. X cross y is z, so I have kx z, and then z cross y is minus x. So there's minus kz x. I need to match the tangential component of h. So for h, I need to additionally divide b by mu. So now we match the x components of the magnetic field on the two sides of the interface. On the left, we have 1 over mu minus kz E. From the reflected beam, there's plus kz. Kz now has opposite sign. Remember, the sign of kz for the incident and reflected, or for generally right-going and left-going in every region. The kz has opposite sign for those two. So then kz E double prime. And on the right side of the interface, I have 1 over mu prime minus kz prime E prime. So kz prime is the value of kz in the region to the right of the interface. Again, a reminder, k parallel squared plus kz squared equals k squared, and k is equal to n omega over c. And k is different in different regions. To the left of the interface, there's n in this expression. To the right of the interface, there's n prime. All right, so now if we take these two expressions, so expression for the matching of the electric fields, it's this one, and this for the magnetic fields, it's two equations with two unknowns. So if we consider E as known, that's the amplitude of the incident light, we can solve these two equations for E prime and E double prime and express the answers in terms of the ratios to E. I'll introduce the notation NZ equals KZ divided by K. And accordingly, NZ prime equals KZ prime divided by K prime. So prime here refers to the region to the right of the interface. It has nothing to do with the real part of anything. So we decided to attach the primes to all the expressions on the right-hand side. So if kz is real, then kz over k is just the cosine of the corresponding angle of propagation with respect to the normal to the interface. In the case of an evanescent wave, nz is an imaginary number. So if now we write the solutions for the set of two equations here and express the results in terms of ratios of E prime and E double prime to E, we'll get the following result. So there's E prime over E, that's the transmitted to incident amplitude. There's 2 n over mu nz, and the denominator n over mu nz plus n prime over mu prime nz prime, and then E double prime over E, I have n over mu nz minus n prime over mu prime nz prime divided by the sum of these quantities. So, if nz is real, then it can be replaced by the cosine of the incidence angle, and nz prime by the angle of refraction. And then these two formulas turn into the familiar Fresnel equations that can be found in any textbook. However, this also takes care of the case of total internal reflection, which occurs if nz is an imaginary number, meaning that kz is not a real but imaginary wave vector. What is the condition for this? The condition is that the value of kz that obtains from this equation in the primed region is imaginary, which means k squared minus k parallel squared is a negative number. Under our assumptions, the wave incident on the left has a real wave vector, so we can introduce the angle of incidence I, and then we can write that k parallel is equal to k times sine I. Now we can use the equation on the right-hand side of the interface to write nz prime squared equals 1 minus k parallel squared divided by k prime squared. I just divided that equation by k prime squared. Now, if I substitute k parallel from just the line above, I'll have nz prime equals square root 1 minus k over k prime squared sine squared I. So in the case where k over k prime is greater than 1, there's a range of incidence angles where the square root becomes imaginary. The expression under the square root becomes less than 0. So this happens at an angle I naught, where sine I naught is equal to k prime over k. This corresponds to the case where the beam is incident on the interface from the side of the larger refractive index. Then there's a range of angles with I greater than I naught, defined by this expression, where there is no transmitted beam, but instead there is an evanescent wave in the region with index of refraction n prime on the right here. This is called total internal reflection, but the equations that we have derived for the field amplitudes is still valid. So you'll have E double prime and E prime expressed through the same formulas. The difference will be that nz here is real, but nz prime is imaginary. In this case in particular, if we look at the expression for E double prime over E, you see that the first term here, the one with nz in the numerator and denominator, is real. But the second part is purely imaginary, because nz prime in the region of total internal reflection becomes purely imaginary. So then you have a ratio of two complex numbers here, which are complex conjugates of each other. Such a ratio has a unit magnitude, and therefore the magnitude of the reflected beam is just phase shifted with respect to the incident one, but it has the same magnitude. That tells us that the intensity of the reflected beam is the same as the intensity of the incident beam, and all the energy gets reflected. Nothing gets transmitted, which of course is reasonable because there is no transmitted wave. It's purely evanescent and it cannot carry any energy. Thus, the formulas that we worked out for the field amplitudes are valid in both cases, whether nz prime is real or imaginary. The field amplitudes can be obtained from these expressions. The other possibility, the other polarization, where the electric field is parallel to the plane of incidence, can be worked out in a similar way, and the result would be the same. You can take the Fresnel equations, derived usually under the assumption that all the wave vectors are real, and simply use nz prime instead of the cosine of the corresponding angle. That would be the angle of refraction in this case. In the second part of this lecture, we'll turn to the analysis of more complicated optical systems that involve more than one interface.